Young's modulus, which is also known as the elastic modulus, is a mechanical property of linear elastic solid materials. It defines the relationship between stress and strain in a material. Young's modulus is named after the 19th-century British scientist Thomas Young. However, the concept was developed in 1727 by Leonhard Euler, and the first experiments that used the concept of Young's modulus in its current form were performed by the Italian scientist Giordano Riccati in 1782, predating Young's work by 25 years. The term modulus is the diminutive of the Latin term modus, which means measure. A solid body deforms when a load is applied to it. If the material is elastic, the body returns to its original shape after the load is removed. The modulus is linear if the ratio of load to deformation remains constant during the loading process. Not many materials are linear and elastic beyond a small amount of deformation. Her constant Young's modulus applies only to linear elastic materials. A perfectly rigid material has an infinite Young's modulus because an infinite force is needed to deform such a material. A material whose Young's modulus is very high can be approximated as rigid. A stiff material needs more force to deform compared to a soft material. The Young's modulus is a measure of the stiffness of a solid material. Do not confuse stiffness with strength. The strength of material is the amount of force it can withstand and still recover its original shape. Material stiffness with geometric stiffness. The geometric stiffness depends on shape, e.g., the stiffness of an I-beam is much higher than that of a spring made of the same steel, thus having the same rigidity. Stiffness with hardness. The hardness of a material defines the relative resistance that its surface imposes against the penetration of a harder body. Stiffness with toughness. Toughness is the amount of energy that a material can absorb before fracturing. Technical. The technical definition is the ratio of the stress along an axis to the strain along that axis in the range of stress in which Hooke's law holds. Units. Young's modulus is the ratio of stress to strain, and so Young's modulus has units of pressure. Its SI unit is therefore the Pascal. The practical units used are megapascals or gigapascals. United States. In United States customary units, it is expressed as pounds per square inch. The abbreviation KSI refers to kips per square inch. A kip is an imperial unit of force and is equal to 1,000 pounds force, making a KSI equal to 1,000 psi. Usage. The Young's modulus enables the calculation of the change in the dimension of a bar made of an isotropic elastic material under tensile or compressive loads. For instance, it predicts how much a material sample extends under tension or shortens under compression. The Young's modulus directly applies to cases of uniaxial stress, that is, tensile or compressive stress in one direction and no stress in the other directions. Young's modulus is also used in order to predict the deflection that will occur in a statically determinate beam when a load is applied at a point in between the beam's supports. Other elastic calculations usually require the use of one additional elastic property, such as the shear modulus, bulk modulus, or Poisson's ratio. Any two of these parameters are sufficient to fully describe elasticity in an isotropic material. Linear versus nonlinear. Young's modulus represents the factor of proportionality in Hooke's law, which relates the stress and the strain. However, Hooke's law is only valid under the assumption of an elastic and linear response. Any real material will eventually fail and break when stretched over a very large distance with a very large force. However, all solid materials exhibit nearly Hookean behavior for small enough enough strains or stresses. If the range over which Hooke's law is valid is large enough compared to the typical stress that one expects to apply to the material is said to be linear. Otherwise, the material is said to be nonlinear. Steel, carbon fiber and glass among others are usually considered linear materials, while other materials such as rubber and soils are nonlinear. However, this is not an absolute classification. If very small stresses or strains are applied to a nonlinear material, the response will be linear. But if very high stress or strain is applied to a linear material, the linear theory will not be enough. For example, as the linear theory implies reversibility, it would be absurd to use the linear theory to describe the failure of a steel bridge under a high load. Although steel is a linear material for most applications, it is not in such a case of catastrophic failure. In solid mechanics, the slope of the stress-strain curve at any point is called the tangent modulus. It can be experimentally determined from the slope of a stress-strain curve created during tensile tests conducted on a sample of the material. Directional materials. Young's modulus is not always the same in all orientations of a material. Most metals and ceramics, along with many other materials, are isotropic, and the mechanical properties are the same in all orientations. However, metals and ceramics can be treated with certain impurities, and metals can be mechanically worked to make the grain structures directional. These materials then become anisotropic, and Young's modulus will change depending on the direction of the force vector. Anisotropy can be seen in many composites as well. For example, carbon fiber has much higher Young's modulus when force is loaded parallel to the fibers. Other such materials include wooden reinforced concrete. Engineers can use this directional phenomenon to their advantage in creating structures. Approximate values. Young's modulus can vary somewhat due to differences in sample composition and test method. The rate of deformation has the greatest impact on the data collected, especially in polymers. The values here are approximate and only meant for relative comparison.